Welcome to this presentation. Today, I will show you our multi-scale framework for simultaneous segmentation and edge detection called HED-UNet. This work is part of our AI for Cold Regions project, or AI-Core for short. So, let's jump right in. This is your typical remote sensing task. We want to segment the pixels in an image into different classes. In this example, we have a Sentinel-1 image of a glacier front in Antarctica, and we want to automatically detect the area covered by the glacier and non-glacier parts. Ideally, we would then end up with a mask like this. In order to understand the underlying process, let's look at how a human might perform this task of pixel-wise segmentation. When we first look at this image, we might be tempted to zoom in on some areas to get a better look at them, and then zoom out again. Most of us will do this intuitively after years of pinch zooming on our smartphones. It just feels natural. Chances are that we'll start with the edge, which requires a great amount of attention to detail. We'll actually spend most of our time and energy on this part, because if we can get it right, we're almost done. Let's give our test subject a few more seconds to finish that step. So now that the edge is done, we would really like to have a bigger brush. This is because we know that the areas farther from the coast don't need much attention to detail, and we can just paint them with this very large brush. So now, finally, we end up with the nice segmentation map that we wanted. However, that took us quite a while, and we're left wondering, can't a computer do the hard work for us? Luckily, in the year 2021, there are existing methods that will do exactly this. One very popular method is the UNet, which is a neural network that works by pushing an input image through a series of convolutional layers. In the first half, the encoder, it applies filters and downsamples the imagery to accumulate information from a fairly large spatial context. In the second half, the decoder, these feature maps are then expanded back up into a segmentation at full resolution. All in all, this process is quite nice and symmetrical. Now, after putting it back to back like this, I hope you're wondering the same thing as myself. That is, can we improve this method by using the observations from the human annotation process? Our first observation was the fact that zooming in and out is tremendously helpful. It turns out that the multi-resolution nature of the UNet already does a pretty good job at this, so we won't change much here. But we see in our experiments that for some remote sensing tasks, the 4 layers in the UNet are too few, so we increase the depth a bit to 6 layers. Now, with the second observation, things get interesting. We humans put a large focus on edges, and that makes sense. After all, there are no shapes without edges, and no edges without shapes. Yet we expect our models to detect shapes without ever teaching them what an edge is. So, let's change that. There are already some deep learning architectures specializing in edge detection. The one I will present here is called holistically nested edge detection, also abbreviated as HED. Like the UNet, it starts with a series of filters and downsampling steps. But then, things take a different turn. From each feature map, the model tries to predict the ground truth. Afterwards, these predictions are all upsampled to the full resolution. Using a learned linear layer, they are then merged into the final prediction. To further boost the performance, the model employs deep supervision. This technique introduces additional loss terms in the middle of the model. Here, this means that the intermediate predictions are also trained to match the ground truth. Now, we want to combine these ideas with the ideas used in the UNet. To be able to do this, let's take a step back to a more abstract view of the network architecture. We remember that the HED consists of an encoder and then a merging head that makes use of all feature maps from the encoder and also handles the deep supervision. Now, the decoder part of the UNet is a great idea because it allows information to flow from the low-resolution feature maps back to the high-resolution maps. So let's put it back in. This architecture is now a generalization of both UNet and HED. So there's good reason to believe that it can take on both the task of segmentation and that of edge detection. There's nothing stopping us now from introducing a second merging head for outputting a segmentation mask. We also promised our model a bigger brush, so now we better deliver. With the learned merging strategy from HED, the merging behavior is the same everywhere. However, it is likely that different weights are needed throughout the image. We believe that fine-grained analysis is needed near the edges, and the coarse, robust predictions should be given a higher priority further inland. Attention is a recently popular technique that does exactly that. It merges features with adaptive weights instead of fixed ones. But contrary to other works using attention, our model will not attend to different time steps or spatial locations, but instead it will attend to different resolution levels. So how can we put that into our model? Additionally to the multi-resolution predictions, we now also predict weights for each resolution level. These are then upscaled just like the predictions. Then we apply a softmax operator so that the attention weights sum up to 1 for each pixel. Now we can use these attention maps instead of the learned merging weights to merge our predictions into the final output. After making all these changes to the model, let's look at some results to see if this model really outperforms the baseline UNet, HED, and other models. We'll start with some predictions in Antarctica, because this is what we developed the model for. On the segmentation benchmark, we can see that the simpler models towards the left struggle with classifications that depend on their spatial context, like the icebergs in the third row. All in all, our HED-UNet performs very well on all different types of scenes. Also, when we compare the edge detection methods, we observe that the existing methods have a hard time in some areas. This isn't very surprising, they were developed for a different kind of imagery after all. We also evaluate the models numerically. Here we show 3 metrics: the MIOU for segmentation, the F1 ODS for edge detection, and the average deviation between predicted coastline and the actual coastline. Interestingly, even the very recent methods don't improve much upon the performance of the UNet, unless edges are introduced. Expanding beyond glacier frontline detection, there are other tasks in remote sensing that also benefit from additional focus on the inter-class edges. As an example, we show the task of building footprint extraction. These are example scenes from the Inria aerial image labeling dataset. You can see that the model puts great emphasis on the shapes of the buildings and that there is little of the ever so prevalent blurriness that comes with vanilla UNet models. Finally, we'd like to check some of our initial hypotheses. We assumed that the model will use the fine-grained predictions near the edges and fall back to these bigger brush, coarse predictions away farther from the coast. Looking at some examples for the attention maps during prediction gives an indication that this intuition was right. From top to bottom, we see the coarsest, a medium resolution, and the highest resolution predictions and attention maps. The very high resolution predictions are indeed weighted very strongly close to the edges, while the coarser predictions are used elsewhere. We can also look at the statistical distribution of the attention values by resolution level. Averaged over all pixels in our validation dataset, all resolution levels contribute towards the final predictions, some a bit more and some a bit less. But when we look at just the edge pixels, we see a significant shift towards the highest resolution. This indicates that the model indeed directs its attention just as we hypothesized. To wrap it up, here are 3 things to take away from this presentation. First, enriching segmentation models with edge detection gives them a better understanding of the scenery. Second, working on multiple resolution levels is incredibly beneficial in remote sensing tasks. And third, even the most recent computer vision models can struggle when applied to remote sensing tasks. Thanks for watching this presentation. Here's a link to our code. If you like this work, make sure to check out our in-depth paper linked below.